David Chum, also co-organiser.
Okay, so thank you, Andrew. So today, this is going to be kind of sort of change of pace, I think, from the past couple of talks. So much less mathematical. There'll be one equation, so it won't be a prize for spotting it. So I'm going to tell you about some work I'm doing over the past couple of years, essentially looking at lyotropic systems, in particular polymer vesicles. So a little background for those, I'm sure will be familiar with most of you. So primarily, I'm going to be looking at diblock copolymer systems. So these are, so it's a, how do I get laser? There we go. So, very detailed picture here. So, you've got a block which is hydrophobic, a block which is canonically hydrophilic. So, these are kind of essentially macromolecular amphiphiles. So, they behave very similar to small surfactant molecules or small lipid molecules. In particular, in dilute solution, they self-assemble into a range of structures. For example, bilayer-based structures, spherical or worm-shaped micelles, and other, perhaps slightly more fancy structures. By the way, can no here make the back? Or good. Okay. All right. Yeah. So very similar to small molecule surfactants, and really the behaviour can be controlled by changing the relative size of the hydrophobic block. Basically, make it more or less hydrophobic, makes changes in phase behaviour. Now I'm going to be interested in looking at vesicles. So these are essentially block or polymer bilayers are folded in on themselves to enclose a sac of fluid. So illustration schematic clear, so you've got some fluid on the inside, some fluid on the outside, and the copolymer bilayer in between. And if you look at it, you can kind of think that's very, very similar to a very simple biological, very simple, cell, essentially. And that has, in a sense, motivated a lot of experimental work. He's trying to investigate these for things such as drug delivery, so we can incorporate both hydrophobic drugs or hydrophilic drugs into these, and then use these as delivery vehicles. Use a miniature reaction vessel, you can kind of encapsulate something in the middle and make something in there. And one reason why there's been a lot of interest studying these is that because, well, two reasons. One is that you can control reasonably well the size of the polymers, so control their properties, but also because the polymers can be quite a bit bigger than lipid molecules, they can be more mechanically stable. And that has also a lot of advantages for certain applications. Now, can I ask, even in that case, if you take a vesicle out of the test tube, stick it into, say, the bloodstream, even doing that leads to great changes in pH, in concentration, and osmotic pressure. And even if you make the vesicle itself a bit stiffer, it can still lead to rupture, still lead to collapse of the vesicle. And so, the natural question to ask is, how can we, in some sense, make the vesicle even more stable, even more mechanically robust? And there are a number of strategies you can think about doing this, and really let's talk about investigating two of these. So first of these essentially is for armouring the vesicle. If you put a coating or something on the outside, for example in this case shown here, coating it with colloidal particles, that will help keep it more robust, help keep things away from the vesicle which you might not want there. Another is the idea of sort of swelling the vesicle. Say you've got something small and hydrophobic on the outside that will then go into the interior of the bilayer, make it thicker, and then if you cross-link that, you can then hopefully make the vesicle again more stable. So this idea of armouring vesicles, armouring essentially these sort of structures in itself isn't a particularly new idea. It goes back actually billions of years in naturally occurring systems. So, for example, many bacteria have what's called an S layer. So it's a highly ordered protein layer that absorbs onto the outside of the bacterial cell wall, bacterial membrane. So, and they can also see there, for example, shown there. So it can be attached onto proteins themselves, incorporated into the cell membrane, or it can be essentially there in contact with other stuff on the outside of the membrane. But essentially, in either case, it tends to make it more robust, and also it can be used, say, signaling or other control of things going into the cell. There are also many algae which form layers of calcium carbonate nanoparticles on the outside. I'm sure many of you have seen a very beautiful picture of this, and so on. It's also a natural question asked if this occurs in naturally occurring systems. Can we mimic this in a synthetic, in a polymeric system? Now, when you ask a question like that, particularly at the beginning of a talk, the answer is almost always going to be yes. And so this is some work that's been done by a collaborating group at Warwick, studying this or rather unwieldy name polymer. I'm not even going to try saying that. So they make vesicles out of these, expose that to a solution containing, in this case, a mixture of 2 different size nanoparticles. They put them in a beaker, mix it around, go away for lunch, come back, and then stick it under TEM. And so this is what they get. So if you look very closely, you see the vesicles under the electron microscope, and you see particles essentially absorbing onto the vesicle, incorporating within the vesicle wall. And that's sort of 2 different examples. And if you look closely, I'm afraid this probably isn't the best picture you have, you see the particles themselves sort of pack on in a very distinctive pattern onto the outside of the vesicle. And so it's a natural question to ask it, from a simulation point of view, is can we reproduce these packing patterns? Can we predict, in a sense, predict these packing patterns? And can we say something about what actually controls this pattern? So to do this, we use some quite simple Monte Carlo simulation. So essentially, the model we use had the vesicle itself, and that's just modeled as a very simple large sphere. So we're neglecting any change to the vesicle shape, any change to the vesicle structure happens as particles absorb onto it, at least as an initial approximation. We also model nanoparticles with a very simple potential. In this case, it's a modified Lorentz-Jones potential, so we change the exponents to make it more short range, more like the sort of canonical depletion interaction. And we add on to that this repulsive Yukawa potential. Essentially, that's a screened Coulomb repulsion. An important parameter here is this parameter A here, which modulates the strength of this repulsion. That's essentially related to the charge density on the particle surface. And say, as we're doing a mixture of particles, we have different sort of equilibrium distances and different essential prefactors depending on whether it's a large particle or a small particle interacting. Now, simulations themselves are again real simple Monte Carlo simulation. We start off with an empty vesicle and gradually add on particles during the simulation. Essentially, it's a random sequential absorption. Now, we neglect particles coming off because experimentally there's a very strong Coulomb attraction onto the vesicle. So while the particles can absorb onto it, they can't come off, but they still move around the particle. Move around the vesicle. So essentially come on, move about, and sort of diffuse throughout simulation. And so this is what we see in simulation compared to what's found in the experiment. So this is a experimental TM images, and these are simulation snapshots. And these are for different, what we call encounter probability. Essentially, that's the probability of trying to insert a small particle. So here the probability of trying to insert a small particle is what's the same as trying to insert a large particle. Here it's about 9 times more often we try to put in a small particle. And what we see is qualitatively, we see quite good agreement between the simulation and the experimental images. So in particular, while it's a roughly equal number of, while the probability is about 50%, you see they quite well mix on the surface of the vesicle. Whereas as we go to inserting many more small particles than large particles are kind of dispersed around, separated out with little small particles essentially uniformly distributed on the particle surface. So as I say, we see relatively good agreement between the experimental results and the simulation results. Now we can go on from that, actually try to, ask what factors can we use to control this packing. And one of the obvious ones is, of course, the charge density on the surface of nanoparticles. And that's shown here as we increase the charge density, as we go from having, in this case, neutral particles to having very strongly charged particles, we see a very large change in the structures formed on the vesicle. And noticeably that no matter what the encounter probability is, no matter how many small particles or how many large particles we try to put on, when you get to very large large charge densities, you see a very similar structure. Explicitly, you see lots of small particles you can fit on, and a few large particles which someone will manage to squeeze on in a gap. And you understand that essentially that for the larger particles, because the charge density is constant, they've got much larger amount of charge on the particles. And so the Coulomb repulsion is much stronger in that case than for small particles. And so it's much harder to overcome that repulsion. So I've shown we can armour particles, or at least experimentally armour particles, and simulation tells quite a bit about how they pack on and how we control that packing. Now the other strategy I mentioned, of course, the idea of swelling and cross-linking vesicles. So if you have a vesicle, then have a sort of monomer, a hydrophobic monomer on the outside, which then goes in, you can then hopefully swell the vesicle, then cross-link that to make it more robust. And that indeed has been tried experimentally, and some results are shown here. Again, these aren't particularly brilliant, I apologise. And so what they see is they sometimes see very nice, very uniformly swollen vesicles, as you would expect, as kind of the aim of what the experiment was. But they also saw some more complex morphologies. So sometimes you see vesicles which got sort of patches on the surface and vesicles which kind of got a coil-type structure on the inside. And so then the question is asked is, what actually is this change in morphology? What's causing this change in morphology? And when is it happening? Is it happening in the initial swelling stage, or just when you expose the vesicle to the hydrophobic molecule? Or is it after that's happening and then cross-linking? And so in order to sort of try to study at least the initial swelling stage of that, I did some reasonably simple, again, simulations, in this case, using DPT simulations, which Mark introduced earlier this morning. So in this, I set up a bilayer of essential coarse-grained polymers. It's a relatively simple model. And I simulate that in solution. And during the simulation, again, I sequentially change some of the solvent molecules on the outside to hydrophobic ones. And then I monitor how, as this concentration of hydrophobic monomers changes, the shape of the bilayer, its bilayer properties change. Yeah. So again, show some simulation snapshots. So this is the bilayer itself in the absence of any hydrophobic molecules. It's just a plain bare bilayer. When you add a few of these hydrophobic molecules in, they rapidly enter into the bilayer. And you see the bilayer swollen a little bit. As I add more, you see the bilayer swells more, but you see these little undulations develop, the sort of ripples develop in the bilayer. But then above a certain density of these monomers, we see a very large change in the structures of the bilayer. In particular, see a little bud of head groups have developed inside the bilayer, inside the vesicle. And it's not shown, but there's also a little bit of solvent in there as well. So it's kind of like the formation of a miniature vesicle inside a vesicle wall. Now we can analyse the structure of the bilayer a bit more quantitatively, so I'll show you some density profiles along the bilayer. So this is the head group one, and you see that shows a very large change as we increase the number of hydrophobic molecules. So it goes from, when there's only a few or none, you see a very well-defined two-peak structure as we expect for a bilayer. But above that sort of budding density, budding transition, see an almost flat distribution of head groups. And that's caused by those head groups folding in to the center of the bilayer. And you'll see that the tail group distribution widens out at the same time. We can also look at the changes to the mechanical properties of the bilayer. In particular, in this case, looking at essentially the fluctuation spectra. So showing the undulatory one, which describes the sort of waves, the ripples, or the peristaltic one, which describes the thickness fluctuations. And in particular, what's important to look at is actually this kind of low Q behavior here. And what I find is as they add more hydrophobic molecules into the system, the peristaltic one just increases. It just gets thicker and thicker and thicker. As you expect, they've got to go in there, so it has to increase in volume. But the undulatory modes, first of all, increases. As I said, you see more prominent waves, more prominent undulations in the bilayer as you add these hydrophobic molecules. But above a certain point, above this budding transition, that then drops again. So essentially, this transition is accompanied by a stiffening in the bilayer. Yeah. Now, the other notable thing about the TM images is that they actually see coexistence of different vesicle structures in the same system. And one possible reason that may occur is that if you look at how the surface tension of the bilayer changes as we change the cross-sectional area, for the flat one that just increases as you expect. But for the when you have lots of hydrophobic monomers in there, you see a much more complex change in the surface tension with cross-sectional area. You see multiple minima along there. And that could explain some of this sort of coexistence of different vesicle structures in the experiment. So, there we go. So, just to sort of sum up, experimental. In this talk, we sort of describes two ways of trying to armour, trying to strengthen polymer vesicles for particular applications. So the first one was looking at armouring vesicles, and as I said, experimentally it's shown it's possible to do this. Shown that simulations, even quite simple simulations, can be used to reproduce the packing pattern seen and actually say a bit about how we can control this patterning. Currently we want to try to quantify the simulation structure a bit more, have more quantitative comparison, try to say a bit about how that changes how absorption particles changes the structure and properties of the bilayer, and also look at more complex particles. Both experimental and simulation have shown that swelling vesicles can lead to a sort of complex morphology in the bilayer. And so currently trying to understand how these formations of isolated blood then leads on to the formation of more complex structures, in particular ones seen experimentally. Now this work's been published for the the armoured vesicle work was published in JACS a couple of years ago. The SWOM work is currently in Press Soft Matter. I'd like to thank various people, particularly Sarah Fortune, they actually did a lot of simulation work on the armoured vesicles. Stephen Bond's group did the experimental work. The CSC at work provided the computational resources, and it was very funded by these people. And I'd like to thank you for your attention.
Thank you very much, David. Any questions? Please,
Right.
For the case where you had armouring of your vesicle, what was the driving force for the particles absorbing?
It was Coulomb attraction. So so the vesicle itself was charged, so that was a catalytic vesicle.
Okay. And what happens, say, for example, if you reduce the volume of the vesicle, like, say, I don't know, using some sort of osmotic pressure or something like that, do you get faceting like you do in armoured emulsion drops? You sometimes see wrinkling or...
So if you can use armoured vesicles and then shrink it down?
Shrink down the volume of the vesicle somehow.
That's a very good question. That's something we looked at. It's entirely possible, yeah. But it's not something...
I mean, I guess it depends how strongly are the particles absorbed on the vesicle interface. I mean, do they ever pop off, or once they're are they irreversibly absorbed?
They should be irreversibly absorbed. I mean, these are TM, so these are definitely done. So these are sort of very much a sort of static picture we have. So I don't think we'd be able to look at whether they then pop off again. But I think you can also kind of estimate what the Coulomb attraction is from the size of the vesicle and from the size of the particles. I think it's probably too strong for them to pop off again.
Okay.
I wonder if you have seen cases where the nanoparticle actually connect to vesicles, you produce them to stitch them.
We haven't seen it. That's a very interesting question. I think might be something to explore, definitely. But it's not something we've looked at.
Mike, did you have a question?
Yeah, I was interested in those surface tension results you reported at the end.
Yeah.
I only caught a glimpse of them, but I was interested in the fact the red line was going down and
Yes.
also ended up negative. Just wondered how you measured that and what that all means.
So this is measured from the integrating the pressure tensor across the standard way. I've not thought about what it means.
Are you having a question? Or was it? I wasn't sure whether you had your hand up. Sorry. Sorry. Any other questions? Okay, in that case, David, thank you very much indeed.